Hi all. So I'm going to give you some more information about Chapter 7. We're going to start with hypothesis testing. So hypothesis testing is when there is a claim that exists and we are trying to use data to compare to a normal distribution or a t-distribution in order to determine whether there is a significant effect based on the sample information. So at this point in the course, as I put a note here, you should not be using any tables for calculations or anything by hand. We're using preferably R, or you may use your calculator. So throughout these notes, you'll see both R code and calculator input if you want to use your calculator. So we're going to stick in the t-distribution realm. And as I mentioned, when you learned the t-distribution in the prior chapter, you learned about some basic assumptions that were required in order to use the t-distribution. And the most important thing is that if the sample size is small, then the distribution of the population from which the sample came should be relatively normal. And so the question that you should have come up with in that last chapter is, what do we do if the basic assumptions are not met? And so the answer is that we can go with some other tests, such as the randomization test or the Wilcox-Mann-Whitney test. And I will be showing you the randomization test first, and I hope that you're going to follow in the textbook on page 223 with the table, because the table is really going to help you. So here's what the table looks like. It's about the comparison of flexibility between those who participate in aerobics versus those who participate in dance. And they were measuring this flexion measure. And there were 4 in the sample for aerobics and 3 in the sample for dance. This top line in here, those were the actual 4 measurements for the aerobics folks. And those were the actual 3 measurements for the dance folks. We took the mean of the group of 4 aerobics. We took the mean of the group of 3 dance. We find the difference of the mean, and this number right here, negative 4.75, is the actual difference within our data. So the real question is, that's one data set and it has a sample size of 7, which is extremely small. So one way to deal with the fact that it is so small is to not trust these results, but to say, what if these 7 data measurements were label-free, meaning put them all on index cards, throw them in a bag, and pick them out of a hat without labels as to if they came from aerobics or dance. And then look at the mean of each of those combinations for the first group of 4 and the mean of the second group of 3, and then look at the difference in means and find all combinations. So that's the idea that we are doing in here. If you notice, there are going to be a total of 35 possible combinations if we have 7 data items and we either pick the first group to be 4, or it is equivalent if we did 7 choose 3 as well. So again, the first line is listed as the correct true difference in our sample, which is negative 4.75. We want to know, is that measurement significant, or is it maybe just due to random chance that it's a difference of 4.75. So if we go back to all 35 results, they start on this page, and bear with me because they do go to the next page. If you notice, the book has handily bolded out any of the differences that are negative 4.75 or more. So you see the first one that's not is negative 3.0 here, and it's not bolded. So go down and, a little fast. So here are the remaining results for all 35. And if you count out the number of bold values, meaning any number in absolute value that is 4.75 or larger, then our result is that there were 20 bolded values out of 35, meaning there were 20 values in the randomization distribution that were 4.75 or larger in absolute value as a difference. So it means that our value of 4.75 for our specific example is not all that interesting, because if we remove the labels and randomize the values, we get something like 57% of them would be expected to be 4.75 or larger. So nothing exciting happening here. So I give you a sense of what this dot plot should look like if there was something significant going on, and it is the reverse. Notice that I put the cluster of all these values are somewhere in between -5 to 5. There are only two values that are 4.75 or larger in absolute value. In this case, I got lazy, I guess, and only put in 23 points, but 2 out of 23 gives us a value of 6.25%, meaning 6.25% of our samples had a value of 4.75 in absolute value or larger. That would be a significant result. So I hope that helps you to understand the randomization distribution. So in conclusion, by randomizing the two groups, dancers and aerobics, flexibility measures, there is no compelling evidence that there's a difference in flexibility between those participating in aerobics and dance. So we're looking for compelling evidence when the number that you get that are of your original difference or larger is a very few set of samples out of a small proportion, I should say, out of the total sample. That is a randomization test. Going on to the regular hypothesis test, if we have difference of means, our null is that there's no difference between the two sample mean values, and the alternative is that there is a difference. They are not equal. And this test statistic, this is your test statistic T that you would calculate manually, y bar 1 minus y bar 2, minus that expected null, no difference, 0, divided by the specific calculation for the standard error. And again, we're not going to do any of this by hand. We're going to do it by technology. So the conditions, again, independent random samples. Samples are from normally distributed populations. We try to check for skewing. If they're pretty small, we are concerned if there's some significant skewing. And you can see, looking at this idea of the p-value, it's the same idea we used back when we learned the Shapiro-Wilk test, that if your p-value comes out as something smaller than 0.01, we have very strong evidence to reject the null. If it's somewhere in between 0.01 and 0.05, we have strong or moderate evidence to reject the null. If it's between 0.05 and 0.10, we have some weak evidence to reject the null. And any p-value that is 0.10 or larger, we say we fail to reject the null. There is no compelling evidence of a significant difference. The t-distribution is very much like a normal distribution. But what we find, again, it's centered at 0. What we find is that the degrees of freedom, which are determined by sample size minus 1, the larger the degrees of freedom, the closer this gets to an actual normal distribution from a t-distribution. It's asymptotic behavior. Again, large p-value indicates the t-test statistic near the center of the distribution. We have a lack of evidence for the alternative. Let me see if I can get that picture for you. Here, if our t-test statistic comes out to something close to 0, then we don't have anything interesting happening, no compelling evidence. Because if you think about it, if you draw a vertical line from your t and calculate the entire area to the right, that's a large area. Whereas, if your t is a large t-value, and if you draw a straight line, you'll get a very small area that it designates. That means that there is a very small area above this t-test statistic, which means that it's more compelling evidence that we reject the null. Okay, so if we continue on, and we say that the null hypothesis is that there is no effect, and the alternative is that there is some effect between the two different groups. Let's look at this example, 7.2.4. We have the example, abuses of substances containing toluene, which is in glue, can produce various neurological symptoms. So they looked at a group of rats, They had 6 that were exposed to toluene and 5 that were the control. So we are examining the mean effect of neurological symptoms of toluene versus the mean effect of no exposure. And the measurement is concentrations of norepinephrine. So just to be sure you notice, in our null and alternatives, we never use statistic notation. We always use parameter notation. So the parameter for mean is mu, as opposed to using x bar, which is a statistic. So what your text has done is they've given you the data, the summary statistics for each, and they've also given you a dot plot of the norepinephrine in the toluene group and the norepinephrine in the control group. If we look at the distributions, this looks relatively normal, although it's only 6, it's hard to see, and this one looks relatively normal, although it's hard to see with only 5. So we're going to say that for now, basically will be okay for fitting the basic assumptions. So we're going to draw, label, shade the curve for the situation. We always put the mean, I'll bring this up a little bit. The mean of the curve is always the center, which is no difference. If we have no difference here, then what we're looking for is that something in the tails would show some effect if we can find that t-test statistic. So we find the test statistic using either your calculator or R, and I will show that next. We state the p-value, and then we write a formal conclusion based on that p-value. So without getting into the details of how we got it, the test statistic came out to 2.345. That is hard to know on the t-distribution scale, so it's a little less meaningful than the p-value itself. The p-value of 0.045, if you go back to what we know about p-values, 0.045 fits right about here. So there's some moderate evidence that there is an effect of toluene on norepinephrine levels. So our conclusion, with a p-value of 0.045, there's moderate evidence that there is a difference in the effects of toluene on rats' norepinephrine levels. And here's your R code. You put in the data sets as a vector for toluene and the data as a vector for control. The command is simple. It's t-test. And the order of these two does not matter, control, comma, toluene, or toluene, comma, control. The alternative is two-sided. That is default, so if you didn't put that in at all, it would already default to that. But you can see here's your p-value, and here's your t-test statistic. If you wanted to do that on the graphing calculator, the steps, stat, tests, choice number 4 for 2-sample t-test, you're going to have an option to click on, it's a toggle between data or stats. So you actually could have put in the data because you were given the raw data values right here. So you could put this in list 1 and this in list 2. If you did that, then you would simply select data and your option would be L1 and L2. But we're going to use the summary statistics, and these are the summary statistics given, and you just enter those. The only thing that we're not going to discuss that's outside the scope of this class is why you're going to choose pooled. You're always going to select no. That refers to something called pooling of standard deviations, and that requires a test that we do not do in this class. Here's another example with crayfish lengths, but what we're going to do is we're going to discuss the confidence interval. So again, we've got box plots for distributions of these 2 different species, one from central Ohio and actually both of them for 2 different rivers in central Ohio. And we're measuring the measurement of units of measurement is length. I'm going to pause here and I will set the next section onto the next video. So that's the end of this part 1.